So looks like we have a hypothesis test here. So this should look familiar. It was a homework problem from last week, but I made a slight twist to it. Many investors and financial analysts believe the Dow Jones Industrial Average gives a good barometer of the overall stock market. And a barometer is actually a thing that measures pressure in the atmosphere, which weather people use to kind of predict the weather. So here they're saying, hey, we can use this to measure the overall stock market. And on January 30th, 9 out of 30 stocks making up the Dow Jones increased in price based on a Wall Street Journal article. Based on this fact, the financial analyst claims that 30% of the stocks in the whole stock exchange, just based on this one sample, also went up that day. So somebody went out and grabbed a sample of 70 stocks that traded on the entire New York Stock Exchange, not just the Dow Jones average. That's just a slice of all possible stocks. And they found that 26 out of the 70 went up. And we want to conduct a study to see if the proportion of stocks that went up is significantly more than 0.3 or 30%. They give us a significance level of alpha is 0.02, 2%. And they also give us the standard error, which we need from a sampling distribution. Okay, so I went out and calculated that, and that should not have a question mark on the end. It is, period. All right, so what do we got going on here? We have a hypothesis. We want to conduct a study to see if the proportion of stocks that went up is significantly more. Okay, so what's going on here? So I write population, parameter, all that stuff. So population is stocks on the stock exchange. Population. And I need to know this if I want to write up an interpretation of the results. Here, I just want to calculate the results, but I'm going to go through this anyway. Okay, I'm going to keep recording. Check back later. So population, all stocks. In the New York Stock Exchange. What am I trying to measure here? That's the parameter of the population. Parameter. And I'm trying to find the proportion that increased in price. Proportion that increased in price. And based on this one analyst, he says he thinks, at least on that day, the proportion of all stocks is going to be like the proportion of the Dow Jones, and he thinks that proportion is 30%, 0.3. That's what he claims. So he's saying it is. So that's a null hypothesis there. And then my alternative is based on this right here. So proportion of stocks that went up. So that part right there is just saying what the parameter is again. The significantly more than, that's the alternative right there. Alternative. So this one was a little bit tricky in that regard. So based on that information, I'm going to say my null hypothesis, this is a proportion, not a mean. P is equal to 0.3, 30%. And the alternative hypothesis, based on this question here, is that P is more. That it's not exactly 0.3, it's significantly more than that. So those are my null and my alternative. Then I have a sample. Sample has n equals 70 stocks. 70 stocks. And the statistic, now the sample isn't 70, there's 70 stocks and somebody looked to see, did it go up or not? So there's somewhere somebody has a spreadsheet that says went up, didn't go up, went up, didn't go up, went up, didn't go up. And they counted X equals 26 went up. So that's one statistic here. The other statistic is P hat, our estimate for what's going on for the whole population. And that would be 26 out of 70. And so I'm going to get that on the calculator next. Google calculator, come here. 26 divided by 70 is 0.3714, 4 decimal places. 0.3714. All right. And standard error. So I haven't taken that into account yet. Standard error is about the sampling distribution. So that's a whole different thing. But that's what we need to make a prediction. So sampling distribution, standard deviation. That's what we call the standard error, SE. I'm given here as 0.055. And once I know the null hypothesis, the sample data, and the standard error, I can now find the z-score. So that's called the standardized test statistic. Standardized test statistic. Standardized test statistic is the z-score. For a proportion, the z-score is p hat minus p over the standard error. So that's the sample minus the population divided by the standard error. So we put the sample together with the population, what we believe about the population, together with the standard error. So those 3 different distributions have to combine together for us to do this inference. So for us, we have that 26 out of 70. You could use the decimal approximation. I lost some decimals there. There were a lot more. I'm going to go with the fraction. Minus the null, which said it is 0.3, divided by the standard error, which is 0.055. All right, so I'm going to type that in my calculator. I think I got those numbers in my head. Correct me if I'm wrong. Oops. So the numerator's got to go in parentheses on this kind of calculator or on a spreadsheet. So that would be the 26 out of 70 minus the 0.3. So there's my sample minus my null divided by the standard error, 0.055. I think I typed it right. I get a z-score of 1.299 to 3 decimal places, 4 decimal places, 1.2987. Let's go with 4, 1.2987. So my z-score, running out of room, I'm going to put it right here. Z equals 1. I'm trying to figure out where to put it. I forgot what it was. 2987. Okay, so now I'm going to draw a picture of this because the next thing I want to do is the p-value. So picture here. Oops, not right for that one. I have a z-score. So when I have z-scores, the mean is 0. 1, 2, that's about 3 standard deviations in the skinny tail there. 1, 2, -3 is over there. My z-score was 1.29-ish, about 1.3. So here's 1 there, there's 2 over there. So 1.3 is going to be about here-ish. Z of 1.2987. And then if I look at the right tail, that area up there would be my p-value. And since I know the z-score, I can use the normal distribution calculator to find the p-value. Now, a couple of the things I'm going to add to this first. Having a z of 0, that's like the null hypothesis. P equals 0.3. This z-score right there was calculated assuming that was the middle and the spread, the standard error, was 0.055. That puts my sample statistic p hat over here, and that was 0.3, was it 3741? About 26 out of 70, yeah, 3741. So now I can see about how far away they are from each other. Now, again, after 2 standard deviations, that gives us a tail of about 2.5%. After one standard deviation, that gives us a tail of about, I think it's 16%. So this is somewhere between 16 and 2.5%. I think I'm going to get a pretty big p-value here. So normal distribution calculator, reset. So I'm in stat key again. Mean is 0, standard deviation is 1, means I'm using z-scores. My z-score down here, right tail, is going to be that 1.2987. which falls right in between, right? 1 and 2 closer to 1, and I get a p-value of 0.097. .097, which we could also say is about 9.7%. That's a pretty high p-value. That's high, which means fail to reject the null. This data is close enough to 30% to say, it's not much higher than 30%, it's just a little bit higher. Fail to reject the null hypothesis. We can't conclude that there were significantly more than 30%. Were there more than 30%? Well, yeah, duh, 37 is bigger than 30. But was it a lot more than 30%? The answer is no, it wasn't a lot more, just a little more. That's our conclusion, or that's our, decision here. Now, I just want to compare. So this was all theoretical based on the z-score and somebody giving me the standard error. The way we were doing this last week was to run a randomization test. I'm just going to compare the results. They're going to be similar but different. So if I go over to stat key, and let's see, what are we doing here? Are we doing a hypothesis test or a confidence interval? We're doing a hypothesis test. Are we working on, so every time I come to stat key, I have to ask myself, which button do I need to push? Okay, so hypothesis test. Are we doing a mean or a proportion? We're doing a proportion. Is it single or a combination? It's just a single proportion. So I think I'm on this page right here. Now, they're not going to have my data here unless I specifically said, hey, grab this stat key data. So I have to edit their data. And stat key says, okay, what's your count? What's your sample size? So my count was the 26 stocks that went up out of my sample size, which was 70. So that's part of using a hypothesis test in stat key. Second part is, what's your null hypothesis? Null hypothesis, 0.3 was the null. Okay, that's the second part. Once I have those two set, I generate thousands of similar samples to the one I had. And I can see they're hovering around 30%, but there's going to be variation. So that's what we're trying to calculate here by just reshuffling this deck of cards in many different ways. And 8,000 should be enough. All right, to find the p-value, I then look back at the sample. Sample was about 37.1%, and I have to put that down here in the right tail. That's the last step here. So right tail, enter your sample data, which is, we entered that right there. We want this guy. 0.371, enter, and I get 11.9%. So it's a little bigger than the 9.7% that the theory predicted. This shuffling the cards 8,000 times produced a slightly different one. If I reset and do it again, will I get a very different number than 11.9%? Answer is no. Based on a sample of size 70, we're probably going to get about the same here all the time. So if I reset, so that was 11.9% for the p-value. Isn't too far from 9% in my opinion. Let's get 8,000 again, and then I say right tail, and enter my sample down here, 0.371, 37.1% of stocks went up for my sample. I get 12% this time. So there's going to be some variation between the randomization hypothesis test and the theoretical hypothesis test that we're running here, but they should be in the ballpark of each other. They're around 10%. That's close enough for what we're doing.